In this lecture, we're going to be talking about linear state space models. Now, if you recall in the previous lecture when we talked about transfer function models, we just tried to find things that were small and chalk them up to disturbances. That worked well for most of our models, but at the very end we had to come to a point where we said, all right, there's a nonlinearity here and we need to linearize about a nominal point. And so we did that for one of our transfer function models. In this lecture, we're going to go over a more standardized approach to linearizing about a nominal trajectory. And this will allow us to use more advanced control techniques. And so we'll go ahead and jump into that. Let's go ahead and get started. So, if you recall, even last time, even when we were talking about transfer function models, we talked about having a function x dot is equal to f of x u, right? Again, just to review, we have our u was delta E, delta A, delta T, and oh, I missed our rudder, right? It went in, we had our forces and moments. Those came out, we were able to calculate our force in the body, our force and moment vectors in the body frame, and we took that in and we calculated x dot. All right, so again, this would also require our x, which we had positions, we had velocities, we have our quaternion, we have our angular velocities, right? Those also are inputs into calculating that x dot. And so these two things together, we can lump them into one and call this x dot is equal to f of xu. So it's a function of our inputs, which then calculate our forces and moments, as well as a function of what our current state is. So we have this nice formulation. We took that and we developed what we called trim conditions, where trim conditions were just developing a nice trajectory, right? And so we talked about how we can use optimization techniques to design trajectories for straight line path, for going up, and for turning in a circle. So we have these nominal trajectories, and we could get desired trajectories from other techniques as well. But the idea here is that we have a desired form for our we have a desired state, and really that's the key here. We have a desired state, and we know what our desired dynamics are. So if we look at the deviation from our trim, so our deviation is going to be small. We want / we will control this to be small. Right, we're going to try to develop a controller that will allow us to converge to this desired state. So again, this guy is being our desired state. So we're going to use feedback control mechanisms in Chapter 6 to start pushing our state to the desired value. So we can look at the dynamics of this deviation. So we're going to use this bar, just like we did in previous lecture. This bar is deviation from the trim, or deviation from the desired. And we can take the time derivative. And when we look at the time derivative, we'll just take, it's going to be the time derivative of x, right, which just comes directly from there, plus or minus the time derivative of our desired state. Okay, so if we look at that, that's f of xu, right? So again, this is just x dot, and if we have our x star dot, our desired derivative, it's just another evaluation of our dynamic function. With our, again, this is our desired state, and this is our desired input. And we saw how we can solve for those previously. All right, we haven't done anything different, but you'll notice is on the left is in terms of x bar, and on the right we have x, u, and we also have our x star, u star. Well, we'll get rid of that all in one form. What we want to use is this relationship. So if we recall, if we look at the definition of our deviation, we could then just write that x is going to be equal to x bar plus x star. And similarly, u would equal to u bar plus u star. And so that's all we're doing here. So we take our x and we substitute that in right here. Sorry, I had to pause there for a second. All I did was I went straight from there to there. In this derivation, we could have just shown that we can add and subtract x star, and we get the same result. But I think it makes more sense. We're just substituting in what our value for x is in terms of x bar and x star. Okay, excellent. This term, we just keep propagating it down, and it comes down. So we now have this formulation, which is very helpful because we have our nominal state plus something small, right? So this is small. Our nominal input plus something small. And anytime we think of having a function of around a nominal plus a something small, when we think of something small, we can think of using Taylor series expansion. So that'll allow us to write up our dynamics in terms of just linear components, and we'll just assume that if it's small, around that small region, then the linear components of the dynamics are going to dominate. So what we do is we come in here and we say, well, using our Taylor series expansion, this guy, and I'm going to erase those components, right, just so I can keep writing. This right here, oops, is, and we'll say this right here. Right, those things, that's our Taylor series expansion. So we're just expanding that one function. When we expand it, we'll get the nominal, plus we'll take the partial derivative of f with respect to our state, so that's this term, and we evaluate it at the nominal. So this component right here is constant. And then we multiply it by x bar. And then we'll take our df du, evaluated at the equilibrium, and we'll multiply it by our deviation, u bar. Again, this is another constant. And it's a constant, these are constant matrices. Okay. And then we'll chalk up everything else to higher order terms. And these higher order terms will include, this will include x bar squared, x bar cubed, and this will actually be 1/2, 1/6, plus, and it'll also include a term that'll be 1/4 factorial, x bar to the 4th, right? And if x bar is small, and if we can think less than 1, right, then x bar squared is going to be smaller, and we're dividing it by 1/2, right? So we have two components there that make it even smaller. And we can look at the higher order terms. 1/6 is even smaller times x bar cubed. If x bar is small, less than 1, then x bar cubed is going to be even smaller. So that's why we say, hey, you know what? If we're small enough, then all of our higher order terms are small. So these are just what we're chalking up to disturbances, right? And we could say the same thing about u bar. as well as cross terms between u bar and x bar. Okay, so this is really cool. So if we take a look at this, we have evaluated our nominal first, and then this guy got propagated down, and we have a minus f evaluated our nominal. So these two are going to cancel out, and we're going to assume this is small, right? These higher order terms are small. So we end up getting that our x bar dot is approximately equal to the partial of x with respect to x, again evaluated at our nominal trajectory, plus the partial of f with respect to u, again evaluated at the nominal trajectory, times u. These, again, are just constant matrices. So we get this nice form, ax plus bu. Now I want to jump in and let's talk about what df dx is. Okay, well first, if we come up here, we can note, well, when we talked over here, f is equal to x dot. So this is going to be equal to f1 evaluated at xu, f2 xu, all the way down to, we have either 12 or 13 depending on the model, if you're using Euler coordinates or quaternions, right? So let's do, we'll do the Euler coordinates, we'll do x, u. Okay, so we have 12 different functions. It's important to note that f is just a vector. So when we look at that, we come down to evaluate what the partial of f with respect to x is. What we're going to do is we're going to take the partial derivative of f1 first. So we'll write df1, and we'll take the partial with respect to dx1. df2, now df1, dx2. And we'll keep going until we get df1, dx, I'll put n, where in our case, n is equal to 12. And then we do our second row. We say, all right, df, now f2 is just that second function. And we're going to evaluate it. We're going to take the partial with one variable at a time, right? With x1 first, x2, all the way up to xn. And we come down here, and we keep going until we get to dfn, dx1, and we'll evaluate that nth function all the way down to dfn, dxn. So that's our partial with respect to x. Okay. We also have df du, where if we say that u is in our m, in our case, m is equal to 4, we have the 4 control inputs, would say that we have, again, we're going to do f1, because that's our first row, and we'll do with respect to u1. df2, I keep wanting to do that, df1, du2. df1, dum. And this one will go down, we'll say df2 now, du1, all the way up to, and we'll do df2 with respect to um. So our final control, all the way down to df, now there's n functions, so there'll be n rows. And there's going to be m control inputs. So there'll be m, as in Mary, columns. So that's what df dx is and df du. Okay, so, and we're going to evaluate these at our equilibrium, right? So they end up being constant matrices. So we'll evaluate all of these partial derivatives. We'll evaluate at x star, u star. We'll evaluate these at x star, u star. Okay, so that's where these functions come into play. Excellent. So we're going to split it up still between lateral and longitudinal functions. So right here, there should not be a dot. This should just be x lateral. So we're going to say that our lateral states are going to be VPR and then phi and psi. And then our lateral inputs are delta A and delta R. Okay. So recall our nonlinear equations of motion, where we can also include, we'll talk about including beta here in just a minute, right? And our airspeed is just the square root of u squared plus v squared plus w squared. So that's, again, assuming no wind. Okay, so these are, just review, these are our nonlinear equations of motion. And you can see that they are definitely highly nonlinear, right? And we need to, yeah, so we've plugged in beta in all of these equations, right? Just so that we show the dependence on the variables that we're interested in. So then we take the partial derivative. So df, we're going to take our lateral functions with respect to our lateral states, right? And so here we've drawn it up, and you can see that first row is we're taking, so this would be our df1, dx1, right? dv dot with respect to v, this would be df1, dx2, all the way up to df1, dx5. Okay. And this guy down here would be our df5 with respect to dx5. So that's the same form that we had before. So we can take our partial derivative with respect to x and with respect to u, and we evaluate them at the trim state. So one thing that I want to emphasize is that you need to make sure you're evaluating this at x lateral star, u lateral star, right? These should be constants. Constant matrices. And again, this one is evaluated at x lateral star, u lateral star. Okay. So we take the partial derivatives and evaluate them at the trim state and trim input. Excellent. So then we end up getting this nice form where this is again our A, this is our X bar, this is our B, and this is our U bar. Okay, so we're evaluating everything appropriately, and the book has already derived all of the individual block matrix components, right? So if we just chose one, LP is right there. So all it's done is taken all of these all of these partial derivatives and chalked them up into, or not chalked them, and defined the block matrix elements. Okay. Now, we can alternatively define things with respect to our beta, right? So if we've seen this relationship before where V is equal to VA sine beta in no wind conditions, right? And so what we can say is that V bar then is going to be VA star cosine of beta star times our beta. Just a sec. Sorry, I had to remind myself where this relationship came from. And it's really just if we consider V as a function of VA and beta, then we're going to linearize again around the nominal point of VA star plus VA bar, and beta star plus beta bar. If we assume that VA is constant, so we're really not varying that much, and we see from our sims that we are able to keep VA fairly constant, then this component right here is just a linearization about that beta. And so the constant term makes that go to 0. And so then if we just do our Taylor series expansion about beta, then we get this equation right here. So again, this is all for, we're linearizing things and assuming that deviations are small, right? So if we take the time derivative of both sides, then we can solve for a time derivative of beta in terms of v. So there you have it. We can then take our dynamics and replace that v with a beta. So we can include, if we're wanting to control our side slip angle, we can throw that right in. Okay, and alternatively, you could have, we know a nice equation. We could have just solved for beta as well, since we're linearizing anyway. Okay, so then we jump in and we look at our longitudinal state space equations. And again, that shouldn't be an x dot. This should just be an x ln. Our longitudinal, wow, that was really ugly. Our longitudinal states, we're going to use u, w, q, theta, and h. And our longitudinal inputs, we're just going to use delta E and delta T. So the nonlinear equations of motion, again, given from before, where now we've plugged in values of alpha, right? So you can see all these inverse tangent terms. So we've actually plugged in what alpha is in terms of our states. And we've also used VA. We've plugged in our VA in terms of in a variety of locations, right? Okay, so there's our VA. And we're using this approximation that there's very little slip in the y direction. Okay, so similar to before, we're going to be able to define our Jacobian matrices, and we're going to evaluate these at our x ln star, u ln star, right? So that they can become constant matrices. And we don't want to forget that. And we take the partial derivatives, and like we just showed, evaluated the trim input, and we can get our longitudinal state equations, where again the block elements, right, xw is already defined for us. So it's all the math has been worked out in the book, but we get this block component matrix. So again, this is just our A, and this is our B. And this is our x ln deviation. This is u ln deviation. Okay. Excellent. So then we can jump in, and a very similar thing to before. If we want to have alpha instead of w, we can do a very similar thing to before, where now we include alpha in our dynamics, and we have the block elements already defined there. Okay, so there you have it. We have these state space representations. Again, we've done a much more formal linearization, instead of just looking at all the equations and deciding what things are small and putting everything else in disturbances. Now this time we've actually just come in and said, hey, here are our dynamics. We're going to linearize about our nominal operating point, and we get these linear equations that we can then work with. And we'll use those in two ways. One, we can develop more advanced control design methods. We can use more advanced control design methods with them. And we can also use them to help us evaluate how our system's going to behave.